So, good afternoon, ladies and gentlemen. I hope you're all doing well. So, welcome to our third tutorial in this series of tutorials. As you know, that we're going back to this basic demand equation for consumer goods, and we have stopped last time on question number 5, or not this question 5, this question 5, which is add the log population, which is the logarithm, the natural logarithm of the population, to the equation. Okay, so what we need to do is to add the natural logarithm. So here I'm gonna be adding the natural logarithm. So here, let's say we have to add plus, and we have to say, let's say it's gonna be beta z log of z, where z stands for population. So I'm gonna choose another color. This z over here stands for pop in your question. And the question was saying is that as follow: is the effect of the population significant? So the first thing we want to do is to test if this effect of this beta z is significant. So what we mean by significant is that is this beta z, so our null hypothesis would be initially, is beta z equal to 0, or it is the alternative, which is beta z not equal to 0. Okay, so we want to do this test to test if it is significant, and we can do this in TSM. So let's go ahead and open TSM. So to my knowledge, TSM, let's open it here. So I'm gonna wait for it. Okay, so we want to continue, let's say. Okay, so we have food over here left. Okay, so we want to run this regression, which we are selecting our dependent variable to be pfood, right? So is it pfood, or so we have to check our previous node, which is food, right? It's not pfood, it's gonna be food. Our dependent variables are gonna be pfood, and it's gonna be qfood. So it seems that I haven't saved it from last time, so that should be fine. I'm gonna be uploading it, but I will get back to you in a minute after I do the same steps that we have. So what I have done right now is that I recreated all the data set right now. And the other thing I forgot to tell you always is to file save, so settings, save as. So you can save it anywhere, but I usually prefer to save it in a place. So what I do is that I do the desktop, I have a shortcut. So I called it food.tsm, so I saved it over there. So now whenever I close it, I can open my tutorial here, which is my tutorial folder, and open this food.tsm. And then everything is loaded, as you can see here. The dataset are loaded. So now going back to our initial conversation where we were thinking about we have to test beta z is equal to 0. Remember what each and every value stands for. xt stands for food, pt stands for pfood, q stands for qfood or qfood, and y stands for the income. Okay, so y stands for the DPI. Okay, so let's now run the regression, but we have to also introduce this POP, which is a population parameter. So we select the dependent variable to be food, the regressors to be, we have to have an intercept, we have to have pfood, we have to select for the qfood. Oh, we have to choose a logarithm, right? So log food, not pfood. Sorry, log pfood. But then we have to remove this and put log pfood, and then we have to log qfood, and then we have to say log DPI. And then what we want to do is we have to add the log population, log pop, and then we hit go with the intercept. So we hit go and we look at the log pfood over here. Log, not qfood, we are looking at log population, which is this. And we can see that this p-value is greater than 0.05, and therefore what do we say? We fail to reject the null, and this means that if we look at this data over here, we can see that it is we are in favor of this rather than that. Okay, so we know that we think that it has no significance. But if we go on and look at the question is asking us the following, right? So if we go to question 5, it is asking us the following. If the coefficient of the log pop is equal to 1 minus beta y, so what they are saying is that we are restricting the beta z. So now it is another alternative hypothesis where beta z is equal to 1 minus beta y. So we are looking at beta z equal to 1 minus beta y. So to test this, if we insert, let's say the null hypothesis is true, okay, and basically the alternative is that this doesn't hold, right? So the alternative is that beta z is not equal to 1 minus beta y. So remember this, we have done something very similar previously in the previous tutorial, which we were testing for beta p plus beta y is equal to 0 if equal to 0 or something like that. This is very similar in the form, but you can do this on your own. But what I really need to say is the following. So if we have this to be true, and we go back here, if we have the eraser, and we erase this, so I'm just wanna show you some steps. So if we erase all of this, okay, we can see the following. So if we selected this color, and then we said the following, so if this is equal to 1 minus beta y log zt, of course we have an error term ut, and then we can multiply this. What do we have? We have log xt minus, so it's equal to beta node plus beta p. So beta p, I'm just gonna copy all of this over here. So let me just erase. Okay, I think I'm better off with the eraser. If we were to erase all of this, and let's just focus on the mathematical part. Okay, so I'm gonna erase this. So beta p ln or log pt plus beta q log qt plus beta y log yt plus or minus, I would say, beta y log zt plus log zt plus ut. So as you can see here, that you have this thing over here, right? So I just defactorize, which I mean by simplify. So I just simplified, I multiplied this by two sides and I wrote them over here. You can see that here we have beta y common. And the other thing is that I have a plus log z over t. I want to take it to the other side of the equality, so it becomes minus. So let's write this down. This becomes, we have log of xt minus log of zt is equal to beta node plus beta p log pt plus beta q log log qt plus beta y of log qt minus log zt, and of course you have plus ut. So now I want you to remember that we have log a minus log b is the same as log xt divided by zt, and this is the same, so I'm gonna keep all of this the same, so just copy and paste over here. The only thing that is different is this guy, so we have to plus beta y, and then we have what? We have log qt minus, so it's the same as log qt divided by zt plus the error term ut. And in this way, we're gonna be seeing that this is what? This is, this is a expenditure by population, by ZT. And over here, you're gonna be having the income. This is Y, by the way. I'm sorry, I copied as Q. So this should be Y. This is a Y. And this is Y divided by ZT, which is the income by, by population. And this is what the question is saying. The question is asking you the following. So if the null hypothesis turns out to be, which is beta Z is equal to 1 minus beta Y, is true, this implies that the expenditure and the income data should be expressed in per capita form. Why? Because of what I just mentioned. And we have to test for this null hypothesis. And I assume that all of you know how to test for this null hypothesis, which is the null hypothesis beta Z is equal to 1 minus beta P. And the alternative would be beta Z not equal to 1 minus beta P. So this is a two-side tail test, and we are gonna go into the details of how to do this. So now that we have set the data, we have to remember that once I've set the data, we have to test for this. Remember, there are so many ways of doing it, but we are just gonna do the the parameter constraint way, which is the wild test. So remember that we need to check the values. So we are looking at this Q, which is number 4. So this stands. We're looking at the population, which is number 3, and we are trying to say that beta Z, which in our case is beta 3, is equal to what? Is equal to 1 minus the beta of P, where beta of P, or beta of income, was it beta of income? So if you go to the question sheet, you will see that this is beta of Y, which is beta of income, is equal to 0. So where is beta of income? Beta of income is DPI. So we're looking at 1, so 3 and 1. So we're looking that beta 3 is equal to 1 minus beta 1. So let's go back here, and we are gonna put the wild here, and we are gonna put the formula, right? We have to put the formula. So we press on model parameter constraint, and then we click on restricted code, right? And then we have to enter the code. What is the code? It's gonna be A3 is equal to 1 minus A1. Okay, so we press OK. And just remember, just double check that we are talking about this is 3 and this is 1, so we are right, I think. And then we have, we just entered the code, so we go and run the regression. So these are the independent variables, it is the dependent variable, just double check. And then we hit the wild test constraint, and then we press go. So we see that this is a chi-squared, right? So this is a chi-squared. And then if we want to test the null hypothesis, we just have to look up values, look up the critical values of a chi-squared, and obviously we have to put the number of restriction, which in our case is 1, and we have to enter the tail probability. So we are talking about 0.05, and then we ask for the critical value. It turns out to be it's 3. So this value is greater than that value, so we reject the null hypothesis that beta Z is equal to 1 minus beta P. Okay, so let's go back to the question that we are talking about. I would like to explain some idea before moving on. Now, here they are saying a time series assumes that the model is constant over time. But there is a number of reasons why this might not be true. The model could shift with a passage of time due to the changes in consumer tastes, or changes in the quality or diversity of the good, or other exogenous extraneous factors. The demand for tobacco may be influenced by medical warning on health risks. So obviously people will start to refrain from using tobacco. The demand for gasoline may be affected by the imposition of national 55 mile per hour speed limit in the US. Okay, so there are things that would have affected the market. Now let's remember me and you together